Hello and welcome to our ionic bonding part 1. We're going to go over naming and formula writing for simple ionic compounds. In order to talk about ionic bonding, we have to start with a definition of what an ionic compound is. So an ionic compound is a compound that's going to chemically combine a metal with a nonmetal. In an ionic compound, you have ionic bonding, which means you have electrons transferring from the metal to the nonmetal. So you're going to have a change in charge. So let's take a look at sodium, and we're just going to use the valence electrons for sodium, and chlorine, which has 7 valence electrons. This is a little wobbly, I apologize for that. Okay, so what's going to happen is chlorine has 7 valence electrons and sodium only has 1. So according to this definition, this single lone valence electron is going to transfer from sodium to chlorine. Now remember, when that metal loses that valence electron, it drops down to having the same valence shell as the previous noble gas. So it's very stable, giving up that 1 valence electron. And as you remember again, so now sodium has no electron. It lost a negative charge. So now it has 1 extra proton, so it has a positive 1 charge. And that chlorine now has 8 valence electrons. And as you remember, chlorine is a halogen. It has 7 valence electrons, high ionization energy. Okay, you're not going to be able to take any of those valence electrons from it. And it stole that electron. So now it has an extra negative charge, or a -1 overall charge for that. And it's that difference in charges that's due to the transfer of electrons that actually holds those two elements together. All right, so let's go through the rules for writing ionic formulas, and I want to draw your attention before we start to these charges that are sitting above. You should already have your periodic table labeled with these charges. So your alkaline metals have a +1 charge, your alkaline earth metals have a +2 charge, and remember that these charges are based on how many electrons are in the outer shell, and the fact that these metals give up their electrons to have a more stable noble gas configuration. Boron family is +3. Now here's where it gets a little tricky. The carbon family is +2 or 4. Nitrogen family is -3 because it has 5 valence electrons, so it will accept or gain 3 more electrons or 3 negative charges to become stable like a noble gas. Oxygen family is -1. Oxygens are -2, halogens are -1, noble gas is 0. So just a reminder, because we're going to need those charges to do our formula writing today. So the first step is to write the symbol of the metal from the name, and then you're going to write the symbol of the nonmetal. Okay, we're going to get all these notes out, and then we're going to work through some examples using these steps. You're then going to label the charges on the symbols. Those charges are very important because they're going to dictate what the subscript is, or how many of that particular element we need in order to get us a neutral compound with our charges. We'll then take those charges, and we are going to drop and swap them into the subscripts. And I'll show you what I mean by that in just a moment. What we want to be very careful and cognizant of is that the sum of your ionic charges needs to equal 0. We are forming neutral compounds, and that's very important for ionic bonding. All right, as a reminder, never, ever, ever, when you're done writing the formula, should you have any charges written. So make sure you get those fully erased. Let's go through some examples. So, starting with lithium oxide, I'm going to write in a darker color. We are going to write the symbols first. So here's the symbol for the metal, and here's the symbol for the nonmetal. The next step is to write the charges. So looking on my periodic table, lithium is right here. Okay, so that is a +1 charge, so I'm going to go ahead and write +1 for the charge. And oxygen is way over here, which has a -2 charge. Okay, so I've written these symbols with the charges. Now I'm going to take those charges and I'm going to drop and swap them to become the subscript for my neutral element. So what I have now is lithium 2 and oxygen is 1. Now, you can write 1 when you're beginning, just to remind yourself that, well, the charge of lithium was 1, but usually we don't write 1. It's considered, you know, if you have it present in your formula, there's at least 1, so 1 is assumed. Okay, so what this is telling me is that I essentially had 2 lithiums with each one valence electron, and I had one oxygen that had 6 valence electrons. So what this is telling me is that that lithium donated or gave its electron to oxygen, and same thing with the second one. So each of these lithiums has a +1 charge, and oxygen took on 2 electrons, so it had a -2 charge. So to write the neutral formula, I will need 2 lithiums, so those 2 positive charges, to cancel out the -2 charge on my oxygen. All right, let's work through another example. Let's do calcium sulfide. So the symbol for calcium is Ca, and it is right here, so it has a +2 charge. And sulfur is right here, and it has a -2 charge. Okay, so our next step is to drop and swap those charges. So I have Ca2S2. All right, so here's another tricky rule. When your subscripts are equal, okay, they're in a 1-to-1 ratio, or if they're both divisible by the same number, you're going to go ahead and do that. So what I'm really saying here is that I am joining calcium sulfur in a 1-to-1 ratio. Okay, one has a +2 charge, and it donates those 2 electrons to the sulfur, which has a -2 charge when it accepts those. So be careful that you reduce those if they need to be. Our last example is magnesium fluoride. Magnesium is an alkaline earth metal, so therefore it has a +2 charge, and fluorine is a halogen with a -1 charge. My next step is to take those charges and drop them to form the subscript for my neutral compound. So this becomes magnesium, and remember, I don't write the 1, and the fluorine is 2. So that means for every 1 magnesium, I need 2 fluorines to accept one of each of those electrons. So now we're going to work backwards, and we're going to talk about how to name ionic compounds. So first, you're going to start by naming the metal. Nothing about the metal's name is going to change straight off the periodic table. Then you're going to take the stem of the nonmetal. For example, if I had chlorine, the stem of it would be chlor, okay? And I'm going to change the ending to IDE. So chlorine becomes chloride. So I like to think of my ionic compounds like being a traditional 1950s marriage between your metal, okay, who gets to keep his name, and your non-metal, the girl who has to change the end of her name. Okay, so let's try this and see what this looks like in practice. So first we have aluminum as our metal, so we're going to write his name as is. We're not changing anything about it. This is aluminum. Then we're going to write our nonmetal, and we're just going to take the stem of the nonmetal, okay, which is ox. Some of these are kind of funky. It's not like it's always INE that you chop off. Like, for instance, oxygen doesn't have INE. So some of this is just going to take practice, and you'll get the hang of where to chop off that name. And so we're going to replace the end of oxygen with oxide. So Al2O3 becomes aluminum oxide. For our second example, okay, our metal is calcium, so we write that as is, nothing fancy. He doesn't have to change his name. And bromine is going to change, so we're going to start with the stem of bromine, just like chlorine is BROM, and we're going to take that INE and we're going to change it to an IDE. So when in a compound, that bromine becomes bromide, so this is calcium bromide. And in our last example, we're working with potassium and oxygen. So I'm going to write out the metal, potassium, and I'm not going to change a darn thing about it. So we have potassium. And then oxygen, we're going to drop the ending of that name and we're going to change it to oxide.